Come on, there we go. All right, so let's start out with the classic. Are there any questions?
Yes. I know you had a little blurb about 44, but I was hoping you could explain that in person.
Live before your very eyes?
Yes.
Somewhere, there we go. This is, that's the wrong book. I don't have those questions with me here right now, so.
Yeah, I have it on my laptop.
I got the problem set from the book we used 10 years ago.
So, he said, let's see here. So this is 44.
All right, so naturally occurring charge on the ground on a fine day out in the open country. All right, so we have a surface charge density.
Can we pull this closer?
Oh, yeah, sure. Yeah. And then there's the blurb, you wrote about it too.
Okay. So that was the charged field. All right, so if I have an infinitely charged plate, and based on the comment, I didn't read the rest of the text, but I assume it's a negative, was a negative charge on the
Yeah, it was
ground?
negative.
So what was sigma?
-1 times 10 to the -9th coulombs.
Per square meter?
Yeah.
All right. So if I have an infinitely charged plate, infinitesimally thin, which is actually part of it, I have an infinitesimally charged plate here with negative charges basically scattered. Then the electric field that comes off of it has the magnitude of sigma over 2 epsilon sub naught. We used Gauss's law and showed that that was true, and then sigma over 2 epsilon sub naught. In the parallel plate, I've got a positive charge and I've got a negative charge here. That there's an electric field going off the positive charge. It goes on forever. So for the positive charge, it's sigma over 2 epsilon sub naught. And then the negative plate has electric field lines going towards it. Of sigma over 2 epsilon sub naught.
And where did and this might have been from the derivation, because I know in the formula sheet it was just sigma over epsilon sub naught. Where does the 2 epsilon sub, or where does the 2 come from?
The two, when you actually derive, when you have the infinite sheet of charge, when we derived it, there were 2 caps there.
Okay.
And that's ultimately where the 2 came from.
Okay.
Do you want me to zip through that quickly?
No, that's okay.
Okay. So when I have the 2 parallel plates, in the region out here, the electric fields are going in opposite directions. So the total electric field is 0.
Okay.
Over here, same issue, the electric fields are in opposite directions, 0. But in the middle, they're going in the same direction, so I have sigma over 2 epsilon sub naught and another sigma over 2 epsilon sub naught. So my total electric field is just sigma over epsilon sub naught, because you just add them together.
Okay.
That's where the 2 disappears.
Okay.
The other time in which you can get rid of it, if I have, for practical purposes, an infinite sheet with 2 sides. So here, it's an infinite plane, it's one-dimensional, or infinitesimally thin.
Yeah.
This is not infinitesimally thin. So if this is covered, if it's a conductor and I have it covered in charges, I got negative charges on this side, and down here, negative charges on that side. And those are all supposed to be negative signs. This plate has an electric field going towards it. Of sigma over 2 epsilon sub naught. And the other side of the plate, because remember, that if it's an electrostatic equilibrium, all the charges on the outside, or sorry, better wording, on the surface. So this one has going towards it sigma over 2 epsilon sub naught. This time, in the middle of the plate, they're going in opposite directions, so my electric field is 0 inside, which should be true anyway, because for a conductor in electrostatic equilibrium, the electric field inside is 0. Out here, I've got the electric field combined. One of them is going towards this side, one of them is going towards that side, but they would combine to be sigma over epsilon sub naught total.
Okay.
Same thing over here. So, if I have a finite thinness to the plate, and the plate's large enough, I can get away with this sigma over epsilon sub naught being the electric field.
Okay.
In that problem though, they said I have a large field here with a surface charge density.
Uh-huh.
To me, that is closer to this than it is to, I've got this negative charge up here, and then somewhere below the ground, just below the ground, I got another set of negative charges.
Okay.
And it doesn't strike me as this either, because that means I've got this negative charge here, and then somewhere up in the sky, I've got this positive charge.
Okay.
And I don't believe, I'm having a hard time visualizing what that would be.
Okay, that makes sense. So I guess like on the test, do we need to kind of conceptually understand when we would be able to use, get rid of the 2 or not, I guess?
Yes, that would
Okay.
be good. Typically, I've got parallel plates there.
Right. Okay. Gotcha. That cleared that up for me, thank you.
Okay, good.
And, oh, so one more, so I don't know if this would be impacted, wouldn't I was confused because I thought it was, you take the absolute value and then they had the answer as a negative. Is that because of?
So, when solving these problems, the sign, you can usually think through what the sign's gonna be.
Uh-huh.
Because, well, if you're talking about electric field, then, it's a direction. You think that, it goes away from positive towards negative. And so oftentimes you can just work through the absolute values and then stick in the minus sign at the end.
Okay.
Or place very strict adherence to the math. Just please be aware that if I got, say, 2 points here, 2 charges here, the electric field in the middle, could be going that way or that way or that way. You have to know when you can ignore the minus sign and throw it in at the end, and when you can't.
Gotcha. That was good.
Okay.
Yes. I have other questions on other problems, but if anybody else has.
Any other questions about this one? Harrison, got
Okay.
another one?
Yeah. So number 62.
And I'm gonna have to say
Yep.
it again. I walked out of my office thinking I had all of this, so I have to keep doing this.
I was confused about.
Which one again, you said?
Number 62.
Oh, yeah, that's fine.
I can't scroll. All right,
Oh, I can, if you need me to.
It's to scroll.
is that? I'm looking at the top stuff, that's why I'm messing up there.
Yeah, or
All right, so I got an 8
Yeah.
microfarad capacitor connected in parallel to another capacitor producing total capacitance. All right, so when you add capacitors in parallel, you should be getting a larger capacitance.
Uh-huh.
Capacitance, when you get the definition, Q over delta V. Because capacitors are generally created by a positive and negative plate, sphere, whatever, positive and negative surfaces,
Uh-huh.
the convention is that capacitance is going to be just the absolute value of this. And in that, so if I take two capacitors, put them in parallel, I should be just adding them up. Which is
Right.
what they have there, which is why you got a -3 for the capacitance of one of them.
Yes, I was confused. Why is it not 13? Like, why is it because?
Because you had in parallel here, the equivalent capacitance was 8, no, equivalent capacitance was 5 microfarads. One of these was 8 microfarads, if I recall correctly.
Oh, so okay, gotcha. I didn't, yes, okay. I forgot that it said the total capacitance. I thought I was talking about 2 capacitances. Now it makes sense.
Okay.
Yeah,
And to my knowledge, negative capacitance has no meaning at all,
yeah,
but I'm sure there's been some professor out there who's come up with some theoretical meaning of it, and either the construction of it is not worthwhile, or it's still theoretical, and he's just waiting for someone to figure out how to do it.
gotcha.
But I've not actually heard of any negative capacitance, which is why it's called the unreasonable result.
Gotcha.
Other questions?
I have one more.
All right.
Okay, I guess I need to show you this again on
Oh.
61. This is about adding the capacitances
Okay.
here. I guess, so with the 8, I think is it microfarads?
Yeah, those are microfarads.
So if that was, I guess, so we don't have to, I guess when I originally thought I was gonna have to do that, like a 1 over the 8, but because it's not, like I can just add the 8 because it's not in parallel and there's nothing like on top or below it, I don't know.
Right, it's not in series with anything because you hit a junction before you hit another capacitor, so
Uh-huh.
it can't be in series.
Yeah,
It's not in parallel with another, we have a way of adding single capacitors in parallel, but it's not in parallel with a single capacitor.
right. And then if we move the 8 up here, and so that could there be a problem like that where the 8 was in parallel with both of these? Or would we not
Well,
do that?
sorry, let me just sort of sketch it up so that,
Yeah.
trusting my memory is always a recipe for fun. And that's the 8 microfarad.
Correct.
All right, so when you're saying bring it up to here?
Bring it so that it's in parallel with the one on the left and the right.
Oh, physically,
Physically, like if we.
that doesn't really have any meaning because this is just a representation of it, saying
Uh-huh.
that, you know, if I had 6 capacitors and I was soldering them, that there's some connection here, there's some connection here. Where this physically is in this line is not relevant.
Oh, really? Okay.
So when we talk about parallel, these are in parallel, even if I drew this one over here. Those are
Okay.
still in parallel, because when I go from this junction to this junction, if I pass that way or pass that way, I pass through one capacitor either way, therefore those capacitors are in parallel.
Okay, that was a misunderstanding I had, but now that makes sense.
Yeah, I guess right now it would've been nice if they'd come up with a different word than parallel, but it's what they came up with.
Gotcha.
Does it matter where the probes are on this?
It does, was it, the probes were what, here and here?
Yeah.
Okay,
Yeah, I should have put those in. Yeah, that would make a difference.
okay, and, microfarads is like a farad to the -6, right? And then nanofarads is to the -9?
Yes.
Okay.
Throw that up here in case it's needed. Micro. Right, Wesley?
We, solved this one, it's really not I don't think it's that hard of a problem, but it was on one of your practice quizzes,
So
that one right there.
how much work?
It's
Wait.
this one, yeah.
Like equivalent capacitors, and there is stuff missing from that. Is this one of my old tests?
There's an old quiz.
What is it?
I'll get back, but the internet's not working here.
Yeah, yeah. Well, if I had the quiz, this must have been from the previous textbook,
So.
and, yeah, someone should have challenged me on that. Because there's not really seeing where the probes go. Alright, so, I'll make it up. So we had 2, 3, 4, 16, and,
I can read it off if you need it.
oh, you don't have faith in my memory either?
No, I'm just trying to be helpful if you need it.
Is that it?
Yeah.
Okay. Did I tell you about that summer at IBM? I had a summer job at IBM. And I get a whole bunch I get a stack of papers, I think it was twice a week, go to some other building, get a stack of papers, bring it back, hand it to one of the engineers, who would then get rid of most of it and just walk away with a couple of sheets. And I thought it was silly for me to bring the whole stack back when all it needs is just a couple of sheets. So I said, what are you doing so that maybe I can do it for you and just bring back what you need. And so he told me, and I said, okay, I got it. I had it I got it backwards in my head by the time I went to go do it, and I brought him everything he did not need. Tossed the rest of it away. So that was my memory at age 20. Yeah, it's better now. All right, anyway. So the equivalent capacitance, one thing I don't have in that drawing is where you're actually putting the probes. There is a dot here, here, and here, so presumably in the original problem, it was a little bit more explicit that I left off. But, so I'm just gonna put, let's say the probes here and here. All right, so if that's the case, then find the equivalent. Well, first off, what do we have here? I see that those are in parallel, because I go from one junction to the next and pass through one capacitor each way. This is not in parallel or series with anything because, well, it can't be in series with these because it has a junction there. And it can't be in series with this because I got a probe right there, which in essence is a junction. So all we can do right now is just the parallel. So then this becomes 5, 4, 16. And I still have probes here and here. Now I've got a series, because there's no junction in between these. So 1/5 plus 1/4 is 1 over the equivalent capacitance. So we end up with 20/9 is the equivalent capacitance. And then that would go in, we're replacing that. Now, in terms of putting the probes in here, I went from basically the shoulder pads to the very corner. Down here, right in the corner. As long as this probe is anywhere in this region right here, it's the exact same problem. Same as on this side, anywhere within that region right there, it's the exact same problem, because the wires have no influence on it other than just to connect from one thing to the next. So at this point, I've got a junction here, I have a junction here. If I go through either path, I pass through one capacitor, therefore they are in parallel, and so I just add those up. So it ends up being 18.2 repeating. Microfarads or whatever the units were.
Yeah.
Is that what you were looking for?
Yeah,
Okay.
that's exactly what I was looking for. I think the second question was what was the charge on each capacitor,
Ah, okay.
and the potential difference across it.
I would have to give some other piece of information.
Yeah, it's just, other than other than what's up is on that picture, it just says find the charge of each capacitor and the potential difference across it. That's why I was
Yeah, that-
confused.
Yeah, I can understand that. I suspect what happened, because when I had that textbook, I had some students who would not have let that go. I probably put the correction on the board. Of course, about that same time, I did have a quiz with an impossible answer, which no one pointed out until half the people had handed it in. So as far as charge goes, let's just run through one of those. If I've got, I need some sort of voltage here. So why don't we put 12 volts? Why not? So with 12 volts and a total, and an equivalent capacitance of 18.2 microfarads, whatever the units were. Then the charge, well, I know that C is equal to Q over delta V, and therefore Q is equal to C times delta V. I know the capacitance, I know the voltage across here, and so I just multiply it and I can find the charge. Then that charge gets split up between these two, where most of it's going towards the 16, because it's a larger capacitance, so it can hold more charge. Actually, I could have saved a step there. I got 12 volts going across there. I lose 12 volts going across here, so this would be 12 times that would be the charge on those plates. And then if I went this way, I would lose 12 there. So I gain 12, lose 12. So 12 times 16 would be the charge on that plate. I'm gonna change my voltage to 10 because that math I can do in my head, at least so far. So this would have, a Q would be 160 coulombs, or microcoulombs. Microfarads.